Hi everyone, what's going on? Let's get right to this example. It's about collisions and non-conservative forces. This is one of the, um, let's say, difficult ones, but it's okay. All right, I'll show you how to do it, and you'll see it's not even that hard. This one has two parts. It's a two-part problem. Um, let's work on the first one. It says a massless spring, physics, with force constant 566 newtons per meter is fastened and its left end to a vertical wall, as shown below. The acceleration of gravity is 9.8 meters per second squared. So this is the spring. It's got a force constant of 566 newtons per meter. And so it's attached to this one. But not to the mass, which we'll read right now, okay? So this is the setup, right here. And then it says, initially, the 7 kilogram block and the 3 kilogram block rest on a horizontal surface with the 7 kilogram block in contact with the spring, but not compressing it. Okay, so pretty much this, right? Not compressing it. And with the 3 kilogram block in contact with the 7 kilogram block. The 7 kilogram block is then moved to the left, compressing the spring a distance of 0.3 meters and held in place while the 3 kilogram block remains at rest, as shown below. So now we have a compression of the spring towards the left, just for this mass, right? Just like here. We have this space, this displacement, 0.3, and this one remains at rest. The 7 kilogram block, I'm reading this, is then released and accelerates to the right toward the 3 kilogram block. The surface is rough and the coefficient of friction between each block and the surface is 0.3. The two blocks collide, stick together. I'm going to say that again. The two blocks collide, stick together, and move to the right. Remember that this spring is not attached to the 7 kilogram block. So now the spring is decompressing, right? It's pushing the 7 kilogram block to the right, and it has this velocity. This one is the velocity of mass 1 initial, that is before the collision. This is the notation we have been using. So this is right before the collision, right? So this one, the velocity would be 0. So it's moving to the right and it's not attached to the spring. That is very important because the motion will be to the right even after the collision. So once we reach the maximum displacement of the spring, it has really no effect on the collision. Okay, it just gave the initial push. Okay, and now the question is, the system, well, before the question, the system displaces 0.59, the system displaces 0.459 meters horizontally before coming to rest. Find the final speed of both blocks stuck together just after they collide. Answer in units of meters per second and round to the nearest hundred. Okay, so there's a lot of stuff going on. But let's focus on the question, right? Find the final speed of both blocks after they collide. And the first thing we have to know is, let's highlight, we have a collision. Now, to know which type of collision, I think you guys know, right? It's simple. They stick together. And although that's not a physics definition, we know that if they stick, it's an inelastic collision. So we should write it down, right? We have an inelastic collision. Ideas I'm going to write with blue. I have an inelastic, that's a, whatever. Let me fix my writing pad a little bit. There you go. And we need to find final speed, okay? Normally we would just go back to the table. Remember the table which I gave you guys? This one. And we have an elastic, and this is the math that we would use. However, this is only valid, this works only if we have no external forces acting on the system. And of course, this is not the case. We have friction acting on the system, okay? So we have to include friction somehow. And then we were told that we have a displacement across a distance. Hopefully you guys know where I'm going with this. We know that friction is a force, right? The force of friction. We have a distance from these two. We know that the force acting across a distance has to do with work. And we learned non-conservative forces with work and energy. So maybe you can use energy as well, right? Maybe we can use energy. So these are ideas. Okay. Now, let's think about what's happening. So the system, after they collide, they stick and they move as one thing, as one unit. So you can think of this as a bigger block, right? With bigger mass, 7 plus 3 kilograms. And if it's moving, we have kinetic energy. And then it comes to rest. So it stops. That is, all the energy will be dissipated, and that is something we expect since we have non-conservative forces. Don't forget that we learned an equation for non-conservative forces. So let's write it down, non-conservative forces and energy. Non-conservative forces. And we had kinetic energy initial plus potential energy initial. Oh, I was going to write final. That was my mistake. Plus the work done by the non-conservative forces. In this case, it would be friction is equal to kinetic energy final plus potential energy final. Now, since we know it stops, right, it comes to rest, that means, let's try it again. At the end, all the energy is dissipated. So it's not moving, there's no kinetic, and then there's no potential either. And then some of you might be thinking, well, if we have, maybe we have potential energy, right? Because we have potential energy from the spring. And although we do have potential energy from the spring, that is something, in this case, we're not concerned about how is it that the block, the 7 kilogram block, was moving, what made it move, right? We know that it was because of the spring, but we're not concerned about that. We care about what happens after the collision, okay? So this could have been someone pushing it, anything else. It could have been anything, but in this case, we're not concerned about it. We know it's already moving. So in this case, we're not going to consider the potential energy. Just the kinetic energy, again, this is after the collision, right? That's when we're talking, after the collision. So we only have kinetic energy initial and work done by non-conservative forces. So we have kinetic energy initial because the system is moving, as you know, of course they collide, plus the work done by non-conservative forces is equal to 0, right? We cancel these two. We're going to move the non-conservative forces to the right. This cancels. And we have that the kinetic energy initial is equal to negative work done by non-conservative forces. Now let's think about this kinetic energy. Okay, this is the kinetic energy of the system, right? Of this system. Both masses are the system and they stuck. So this is for the system. Okay, and this is the work done by friction. Okay, so now that we have the ideas and the formula or equation we have to use, let's start with the given. We have a lot of givens, so we should get going with that. Given. Although I know what we need, right? Variables related to these two, I'm still going to write all the given because I may need to use it later. I don't know. The spring constant, the symbol is this funny K. I'm just gonna do a normal K. It is 566 newtons per meter. And then we have well, the two masses, right? So just for the picture, this is mass 1. I'm going to label this one mass 1. And this one will be mass 2. Let's see, mass 2. So mass 1 is 7 kilograms. I know I'm not looking to significant digits. I know. Sorry. 3 kilograms is mass 2. What else do we have? Acceleration due to gravity is 9.8 meters per second squared. We have this displacement. If you remember the equation for kinetic energy of a spring, this is the x, right? Displacement along the x. So we'll have x equals 0.3 meters. Again, that's because the kinetic energy of the spring, this is potential energy of the spring is 1/2 kx squared. This is the distance of compression or stretching, right? Just wanted you to see it. And then we have a coefficient of friction. So it's Greek letter mu, 0.3, just 3, right? No units because it is a coefficient. And then, we have a displacement. So I'm just going to use the letter D for displacement, or you can think of a distance with the direction, right, horizontally. 0.459 meters. Okay, and we need to find the velocity after the collision, and it is an inelastic collision, so we know that the final velocity we'll label as V final. So we need to find V final. Okay. So now let's start with the math, right? We know this is the equation that we need, the kinetic energy for the system. And the equation for kinetic energy, the normal one, right, traditional one, is kinetic energy equals 1/2 mass times velocity squared. In this case, we have more than one mass, right? The system has two masses. So in this case, we'll say the kinetic energy initial. Oh, wait. Well, I can write it like that. Initial, that is, of the system is 1/2. Both masses combined, so mass 1 plus mass 2 times the final velocity squared, right? This is after the collision. I know it's funny, the kinetic energy initial, so that is initially on the system before it stops. That's why you have initial and final. Hopefully you don't get confused, right? So just know that this is the kinetic energy right after the collision. And then the work done by friction, because that's the non-conservative force, is the force of friction. That's the simple force of friction times the distance times the cosine of theta. And we know that the equation for force of friction is coefficient. That's an ugly coefficient of friction. Let's try it again. Man, it's almost identical. there you go, times the normal force. Okay, so we do have a normal force. We have to do a free body diagram, but that's okay. And so now let's substitute. We have 1/2 m1 plus m2 times velocity final squared equals negative the work done by friction, that is force of friction, which is mu, which is the coefficient of friction, times the normal force, times the distance, times the cosine of theta. Before we continue, we need to know what the normal force is, and for that, let's draw a free body diagram, right? Because we have forces. I'm just going to kind of copy the combined mass. Here's fine. Let's make it blue. And you guys know that in this case, there's an acceleration, right? Then there's friction, force of friction. But we are going to start with the weight of the system. So maybe the center of mass is here, about, right? So it's 4. Is it right? Yeah, I think this is good. Right, so that's the weight, which is mass 1 plus mass 2 times acceleration due to gravity. That's the weight of the system, both 7 kilograms and 3 kilograms. And then, there's an equal and opposite force acting against it, which is the normal. Equal and opposite. And then we have the force of friction. If the motion of movement is to the right, we have a force of friction like this. And then the spring applied a force this direction. Again, maybe the magnitudes are not precise, right? So I'm going to call this force by the spring. Force by the spring. But again, we're concerned about this one, right? We know the system is not moving along the y-axis, right? Vertically. So if we sum the forces, we can say that the forces acting along the y-axis are equal to the normal minus m1 plus m2 g, and that is equal to 0. The only way these two can be equal to 0 when subtracted is if they are equal to each other. There you go. And now we know the normal in terms of stuff that we have, m1, m2. The next thing we have to do is substitute. So we'll have, I'm probably going to need more space, 1/2 m1 plus m2 v final squared. Again, this is the final velocity, just so that it matches the collisions notation, right? And then, but truly, it would be the initial velocity, right after the collision. But again, I want you to have this one because this is the velocity of the masses moving together. Okay? And that is equal to negative, and then we have, I'm going to need brackets, coefficient of friction times the normal. I know this is the normal. That is m1 plus m2 times acceleration due to gravity times the distance times the cosine of theta. The next thing we have to do is we have to talk about theta. Okay. Theta represents the angle of the force being applied, and then you have the force of friction moving horizontally, right? Horizontally to the left, and then you have the force applied by the spring horizontally to the right. Both of them are horizontal, so it's either 0 degrees or 180 in this case. Since they are opposites, we learned that theta for opposite forces along the same axis is 180, right? We know that theta is 180 degrees, and this is too crammed in here. There you go. We know it is 180 because we have opposite forces. Okay. And then the cosine of 180 is -1. So we have m1 plus m2 v final squared equals negative coefficient of friction m1 plus m2 times acceleration due to gravity times distance times -1. Hopefully you guys see that this negative and this -1 will turn into a positive. So now we have 1/2 m1 plus m2. I'm going to clean up my equation just a little, right? Letters with the letters. So I'm going to have coefficient of friction times acceleration due to gravity times distance times the sum of the masses. So now I can start solving for velocity final. I want velocity final, not velocity final squared. We'll deal with the squared at the end. So let's get rid of this 2 mass 1 plus mass 2 times velocity final squared equals, let's get the number first, 2 times mu times g times d. You guys know the names of these. Times the sum of the masses. That would divide by the sum of the masses. Man, that was bad. That was really bad. There you go. m1 plus m2. And I'm just going to copy this because why not? Oh, it took this part. We don't need that. There you go. Now this is something very cool. I'm going to keep using purple. So these cancel, but check this out. Ooh, these cancel just the same. So now we have velocity final squared equals 2 times the coefficient of friction times acceleration due to gravity times the distance. And we take the square root to get rid of this square. And our final velocity is, I'm going to do the square root at the end. 2 times coefficient of friction times acceleration due to gravity times the distance. And you take the square root of all this stuff. Okay, let's substitute over here. Velocity final, that is the velocity after the collision. That'll be, again, I'll do the square root at the end. 2 times coefficient of friction was 0.3, no units. Let's try that again. Times 9.8 meters per second squared for acceleration due to gravity times the distance. Now, don't confuse, this is not the distance it would stretch, it's this distance before it came to rest, right? This, 0.59 meters. 459 meters. There you go. And then I am not going to attempt to do this thing, because of course I'm not going to be able to do it. And oh man, not even that. One more. There you go. Whatever. Okay. So let's try that. We have the square root of 2 times 0.3 times 9.8 times 0.459, and we have 1.64. It's set round to the nearest hundredth. That is two decimal places, because 100 has 2 zeros. So 1.64. Our final velocity is, or velocity after the collision would be 1.64 meters per second. And that is part 1 of 2.